All right, so we're going to be going over lesson 13 here on interference, okay? And you guys probably, more than any generation before you, experience interference more, okay? Because the wireless nature of our society now, okay? There's any number of devices that you might have that could be interfered with in some way with their transmitting or receiving functions, okay? How many people have ever experienced a time where they had interference? Right, okay, pretty much all of us, all right? One of the worst ones for me was, well, it's probably now about 9 years ago, something like that, when we had a car that didn't have like Bluetooth and stuff in it, so we had the adapter that would transmit from my phone to the radio. Anyone have one of those in their car? Okay, and it was a cheap one. And I was driving down the road with my two kids in the back seat, and they were watching something on the little video player, okay, that was in the back seat, and it was transmitting through this radio thing into the radio, and all of a sudden the sound starts cutting out. They're watching like something perfectly innocent like Wall-E or something like that, and this low rider car pulls up beside me, and all of a sudden, like the most vile gangster rap starts coming over my stereo, much louder than I had the volume for the innocent movie my kids were watching. So you can imagine how quickly I was fumbling with the controls to get it all turned off. Okay, but what had happened was that the person beside me, okay, had their same transmitter on, okay, to the same frequency. Their waves, okay, their frequency was obviously, or their transmitter was obviously stronger than mine, so their waves interfered, and because they had the same shape and wavelength and frequency, they completely overrode mine. Now, I don't know whether he heard the soundtrack from Wall-E in his car, okay? If he did, that would be somewhat funnier, but okay, all I know is that I didn't hear that anymore, okay? I heard the more overpowering waves that were coming from his transmitter because they interfered with the ones coming from mine, okay? And we've all kind of had experiences like that. All right, so interference is what happens when two waves occupy the same space at the same time. Most of the time, okay, interference just makes waves unintelligible. Okay, it just messes them all up and we can't really tell what they were, right? The thing about interference though is it's not permanent. Interference only occurs where the waves overlap. They pass right through each other, right? And on the other side of that interference, they go pretty much back to normal. All right, so interference is not a permanent thing. You've probably noticed that if you start getting really bad reception, if you move around a little bit, you kind of find a spot that's better. Okay, it's still the same waves. You just found a spot where there wasn't interference. Okay, and that's generally what we want to try and do, okay, if we want to avoid interference. All right, there are two types of interference. The types of interference are constructive. That would be interference that makes the waves bigger, okay? And that there would be destructive interference. That's interference that makes the waves amplitudes smaller, right? And as a result, makes things quieter if it's sound, right? So we're going to look at how that can be applied to practical purposes. Most musical instruments use constructive interference in order to naturally or acoustically amplify their sounds, okay? We use destructive interference to muffle sounds. All right, so if you drive a normal vehicle, your muffler bounces your sound waves throughout, kind of through different perforations and around the inside of the muffler in order to cancel them out using destructive interference. If you drive the redneck mobile, okay, the big truck with the straight pipes, okay, it basically means you have no muffler, or maybe you've just hacked them off ahead of the catalytic converter, so it's basically coming out of the manifold, okay, you're that guy. You're don't have anything that's causing this destructive interference, canceling out, okay, any of that sound, and as a result, you'll receive a noise violation eventually, okay, from the police because you're just obnoxious. Okay. So we've got those kinds of things. Same with if you have like a Harley, okay, you ever notice, when a Harley pulls up beside you, right? Because they don't have any mufflers, the pipes just come straight out of them, okay, and they're really loud. Yeah, I don't really buy that. Baffles, yeah. It makes sense. Yeah, because people don't pay attention when they drive anymore. Yeah, like a lot of people don't. When we were driving up to Edmonton for the West Ed trip, I kind of just looked out the window every time someone went by us, and I swear half of people were on their phone when we were driving up. It was scary. Okay? I just feel like I shouldn't look out the window anymore because it's just scary. Anyway, so we're going to look at the different kinds of interference. We're also going to look at something called resonance, okay, which is a way to make sounds, again, amplify themselves and create, it can create some benefits, but it can also create some problems. Okay, so what happens when two waves interfere with each other is this. Their amplitudes add together, all right? Now, if you have two waves that are opposite, adding them together makes them cancel out. If you have two waves that are the same, adding them makes them bigger. All right, so that's the general principle here that we are looking at. That principle is called the principle of linear superposition, which is a really complex way of saying when waves occupy the same space. Okay, they superimpose themselves onto one another. Okay, they overlap each other. So if I have this situation on the left, I have two pulses. These are not complete waves because a complete wave would also have the down cycle. So these are just two pulses that are approaching each other. All right, so this is kind of the before picture. This is like kind of during, and you can see that the medium, which in this case is a spring, is trying to accommodate all the wave energy that is traveling on it. Okay, essentially, that's what interference is. It's the medium trying to accommodate all the wave energy that is passing through it. So you can see here that when the waves are completely overlapped, the amplitude shown by the medium is double that of the individual pulses. In other words, we've added their amplitudes together. Okay? Their energy is all conserved and represented on the spring. Questions on that part of it? Okay, this is actually a pretty easy concept. We just add the amplitudes together is basically what we need to know. All right, and then the big thing here is that this interference is not permanent. Once they've passed through each other, they keep right on going as they were before. They don't reflect off of each other. They don't destroy each other. Okay, they just pass right on through. Okay, this was energy that was passing through the medium. Okay, because it's not matter, energy can pass right through, okay, itself or another bit of energy and then continue on completely unaffected. Everyone all right with that idea? Okay, the exact opposite occurs if I have an up pulse and a down pulse approaching each other. Okay, well, sorry, not the exact opposite. Mathematically, the same thing. I add them together, but the appearance is the exact opposite. All right, so here they're about to overlap, and here you can see that because we had one energy that was negative and one energy that was positive, okay, the medium is representing that as now the energy has canceled itself off. Right? There's no amplitude, no shape to the medium, and then shortly thereafter, those two original pulses are carrying on about their merry way. White noise is more just kind of anything that happens to be present at the time. It's just kind of haphazard, right? Like noise canceling headphones? Noise canceling headphones use this technology, yes. So they have a small microphone on the outside. Okay, that microphone picks up the ambient noise, and the speaker on the inside produces opposite frequencies that would help to cancel that outside noise. So yes, noise canceling headphones definitely use this idea. Yeah. Okay, but you got a true noise canceling headphones. Lots of headphones say they're noise canceling and they're really just insulated, right? They're against sound from the outside. True noise canceling headphones have microphones on the outside to detect the ambient noise on the outside. Okay. All right, questions on how that idea there works? All right. So one of the things that we have to be concerned with is that waves can actually travel and be set up in essentially any medium. We don't, in some mediums, want that. Okay, especially if many waves can be traveling through that medium at the same time. All right, if I've got, I'll just bring somebody up here and I need someone to hold the other end of this slinky. Okay, who wants to be my volunteer to hold the other end of this slinky? It's a slinky. The spring, a marvelous thing. Everyone knows it's slinky. Come on, it's fun. Okay, if you guys you've never heard that? Have to have heard that. Okay, we'll just put it on the floor. Okay, guys, you might have to get out of your desk so you can see what we're doing here. Okay, can you guys all see the spring? All right, so what I'm going to do is I'm going to make a pulse toward the wall. Peter's going to make one this way. Okay, watch what happens as they pass through each other. Okay, you can see that they didn't get affected by the fact that they passed through one another. They just traveled on. During that one moment where they were interfering with each other, the amplitudes changed, right? That spot on the spring was smaller than either one. Okay, we'll both make one toward the wall this time. Okay, so you can see just for that instant, it kind of hops out and it's a little bit bigger, and then they travel on. Now, they shrink pretty quickly because there's a lot of friction between the spring and the floor, so the wave energy dissipates fairly fast. Okay, but you can still see that that's the stuff that's going on. All right, let's make two toward the wall again here. Okay, so you see that they interfere, okay, and they do that. Now, what we don't want to have happen is if we've got a lot of waves traveling on the slinky, so I'm just going to make waves here, okay? If I've got a lot of waves on the slinky, okay, they'll eventually start reflecting back off the other end, okay? And if that keeps happening, and this is a more efficient system than this, they can start coming back. They have the same frequency and the same wavelength as the ones I've made because they're just reflections. What that can produce is interference that causes the spring to start to move more. Okay? We don't want to have that happen if we're talking about a structure, like a bridge or a building. Okay? If we get waves set up in a structure, then the structure might sway too much and collapse. Okay? Thanks, Peter. Okay, so this is how, especially in places where there's a lot of seismic activity, okay, that this has to be taken into account when they design buildings. Okay, we don't want to get something called resonance set up in a structure. Okay, that is, waves are traveling through it, and they start to interfere with not only the created waves but the reflected waves as well. Okay, so in places like California, they build tall buildings on essentially very large springs. But they put a different weight of spring at each corner, okay? So that any wave that travels through one side of the building can't travel through the other side of the building with the same wavelength and frequency. It'll essentially interfere destructively and cause the wave to disappear, saving the structure. Same with bridges. Okay? We don't want to have a bridge that can start getting start getting these waves resonating on them and cause it to collapse, which I'll show you a video of here in a minute. A bit, yes. Okay, it's also why in the British Army, okay, they have a rule. Anytime they're doing a march and they go over a bridge, they break stride. Okay, so up until that point, everybody's feet are hitting the ground at the same time, up 2, 3, 4 kind of thing. Okay, when they get to a bridge, they stop and everyone breaks stride. Everyone walks at a different pace. Their feet don't hit the ground at the same time, because if they do, they can actually set up a resonant frequency in the bridge and cause it to collapse while they're marching over it. Not anymore, obviously, because bridges are built better than they were then. Okay, but way back in the day, that was the thing. They had to break stride. They still do it as part of their military training. They break stride before crossing a bridge. Okay, so I'll show you the video here of the Tacoma Narrows Bridge. This was built in Tacoma, Washington, across a deep but kind of narrow gorge, essentially. The problem with the bridge was that it had a very long span, but it wasn't very wide. Okay? And so as a result, they couldn't put any pilings in the middle. So it had to be a true suspension bridge, kind of like the Golden Gate. Okay? It had to be a suspension bridge, but winds tended to blow through this gorge, and they set up essentially resonant frequencies on the bridge that caused the bridge to sway, which initially was just interesting. But one day it got really bad. Okay, and you can see what happens when these waves, if they're allowed to travel through a bridge, what they can cause. So I'll show you this here. Okay. So with that, okay, we can see that if waves start to interfere with each other, they can get bigger. Okay, and if that happens, then we can get structural failures and things like that. Even the buildings in downtown Calgary are designed to sway a little bit because obviously we get fairly strong winds through here. Okay, and they can be sustained for hours or days even, and the buildings have to be able to deal with that. Okay, if we built them just perfectly rigid, okay, they would start to get some structural deficiencies and breakage and stuff like that just from the general force of the winds. They're actually built somewhat flexible so that they can sway a little bit in the wind. People who are especially sensitive to that kind of stuff can actually notice that. Okay, there are some people who can't work in the upper floors of a skyscraper. right? Because they can feel the swaying of the skyscraper on the upper floors. They actually get sick, physically sick from the motion of it. Okay? It's pretty rare, but there are people who cannot work on upper floors of very tall skyscrapers. All right, so everyone gets this idea of constructive and destructive interference. Yes? Okay, so just quickly here then, okay. So the principle of linear superposition says that, okay, the slinky or the medium, whatever it happens to be, in this case it was a slinky, okay, it assumes a shape, okay, that is the sum of the shapes of the individual pulses or waves that are traveling through it, okay. In other words, it has to take a shape that conserves and represents all of the wave energy that is traveling through it at any particular time or point. All right, so on the left here, we have an example of destructive interference. Okay, the waves are opposite, so when they interfere with each other, the sum of their amplitudes is 0. This one here would be like +1, this one would be -1, so when we get to here, the amplitude is 0. Whereas in this case here, we have a +1 and a +1, so when they are occupying the same space at the same time, the amplitude is +2 and the energy is all conserved. Is it a wireless sub? Yeah, probably. That's probably what it is. It's picking up other signals that are causing it to do that. The only other reason would be is if you had if it was wired, having a loose wire. All right. So that's the sum of the individual pulses. Okay. We have the two types. Okay, and that this one here. Sorry, these were supposed to be animated, but they're not moving. So this one here would show constructive interference because in a little bit they would occupy the same space and it would be twice the height. And then this one here in a little while, okay, they would occupy the same space and cancel each other out completely. Right. And the same is true for wave trains. Okay, if I have a whole bunch of waves that are traveling along through a medium, okay, and they interfere with each other, then the same thing will happen. So if I've got wave A and wave B here on the left, okay, so here's wave A. Okay, and here's wave B. They're traveling through the same medium at the same time. You can see that they have the same wavelength. They also have the same frequency. Their waves are all the same. Okay, and since they're in the same medium, they're traveling at the same speed. So all the parts of the universal wave equation are equal for these two waves. Right? As a result, the medium has to reflect the energy of these two waves, and as a result, it'll have an amplitude of that is the sum of these two. So let's say this one's like +2, this is like +1, this would be -2, -1, and we can see here that this goes to +3, to -3, and so on. Right? In the example on the right here, we have waves that have, again, the same wavelength, same speed, but they are what we call out of phase. Okay? These waves here, these are in phase. Okay, when one is up, the other is up. These ones are out of phase because when wave A is up, wave C is down. All right, so they are opposite or out of phase with each other, and as a result, okay, our resulting wave is much smaller than either one of them would be alone. Okay, so these are just terms that we have to know: in phase, out of phase. Okay, constructive interference, destructive interference. Okay. All right, same thing can happen with sound. And if you get like a home theater system that's professionally designed and installed, okay, not that probably most of us could afford that, but okay, if you had that, what they do is they generally try to place the speakers and then set up the amplifier in such a way that the places where you sit will experience constructive interference for most of the frequencies that you would hear. Okay, so they set it up that way so that your couch gets really good quality sound, whereas, you know, the hallway to the bathroom doesn't, right? Because you're not going to watch a movie from the hallway to the bathroom, right? But you are going to watch it from the couch. So they'll set it up in that way. So if I'm in a acoustically perfect room, in other words, it's called an anechoic chamber. It's a room that essentially has no echoes, right? This room has echoes. Right, and the walls are smooth. Right, if you go into an anechoic chamber, it's like you're standing inside a meat grinder. It actually looks like that. It looks like something out of a horror movie because all the walls have all these little fins and things like that that are all different shapes to prevent echoes from coming back to you. Okay? If you speak in there, it's really weird. Right? You know how your voice sounds different to you than it does to everybody else? Okay? The reason for that is partially the way it resonates inside your own head and your sinuses and things like that, and because a lot of what you hear in your own ears is the sound after it's traveled through the air, bounced off of walls, and come back to you. The waves alter a little bit when they do that. Okay, so our perception of our own voice is different than that of what other people hear. Right? So if I'm in an anechoic chamber, I would sound a little different. I would sound more like a recording of myself. Okay? By the way, I hate the sound of my voice when I listen to these podcasts. I'm like, I don't know how you guys do it. Listen to me every day. But yeah, so if I'm in an anechoic chamber, okay, and I had these two speakers playing, if I moved around the room, the volume of the sound would change depending on where I was. I could stand here and hear the sound really, really loud and clear. If I move a little bit this way, the sound volume would go down a little bit. Okay? If I took another step in another direction, I might hear nothing at all, even though the sound is still being played by the speakers. Right? It depends on whether the waves are meeting constructively or destructively at various points. Okay? And there would be points around the room where that would be the case. Okay. So in this case here, we've got waves coming from both speakers. The listener is the same distance from both speakers. So as a result, okay, he's hearing the waves meeting crest to crest, trough to trough, and they're always interfering constructively. Everybody all right with that idea? Okay, they're traveling the same number of wavelengths. Okay, it's 3 wavelengths to the listener from this speaker, and it's 3 wavelengths from the listener to this to the speaker on this side as well. Okay, everybody all right with that? Okay, so essentially, he is standing right here. No, sorry, he's standing right here, 3 wavelengths. Oh, that is 3. Okay, so he's standing right there where we've got constructive interference happening. Were he to move to this position, what would he hear there? Okay, remembering that the lines represent a crest. So it might be easier if I do this in the middle. Okay, so anywhere where you see a dotted line is a trough. Okay, what does he hear right there? He's where a crest and a trough meet. They cancel each other out, right? Okay, the waves are meeting out of phase. One is a crest and the other is a trough, so he hears nothing. Okay, at that point, if he was in a perfectly acoustic room, he would hear nothing at all. Okay, absolutely nothing at all at that spot. Okay, this is a behavior of waves. Okay, that is unique to waves. It's also what allowed us to determine that light was a wave. We'll talk about that a little bit later on in the unit. But okay, this is a spot where he would hear nothing at all. If he moved over to this position, then he would hear a loud sound again because now they're meeting crest to crest. Okay, if he was standing right here, he would hear a loud sound because he would be at a spot where there's a trough from one speaker and a trough from the other speaker. Right? They would interfere constructively at that point. At a point, not like completely, but yes, at a point. Now, because light's wavelength is so incredibly short, it's not like you could walk around in a room and go, dark, light, dark. It just wouldn't work like that, right? Like you can dance back and forth between a light spot because the wavelength of light is incredibly small. Plus, it reflects off everything. The experiment that was done to prove light was a wave essentially limited it to a small stripe. And then we could see patterns of light and dark on a screen as opposed to spots on the floor. All right, so that okay with everybody, that idea there? All right, so if I change this situation and now I back this speaker up half a meter, which happens to also be half of a wavelength, now this person hears nothing. It's now destructive interference because instead of meeting crest to crest like it did before, it's meeting trough from this one and crest from this one. So now we have complete destructive interference because now this one has traveled an extra half a wavelength. Okay? Crests and troughs are half a wavelength apart. So if one wave travels a half a wavelength further than the other they're always going to meet out of phase, right? So like here's your kind of classic waveform, right? This to this is one full wavelength. So from here to there is half a wavelength. So a crest and a trough are always half a wavelength apart. So if the distance of travel is half a wavelength, 1.5 wavelengths, 2.5, as long as it's some factor of a half, okay, you're going to have destructive interference. Michael. No, that could just be that it's actually below the threshold of your hearing. Yeah, like for most people, the threshold of hearing is about 20 hertz, which would be really deep, almost you'd basically only feel it kind of bass, to 20,000 hertz, which would be like piercing shrill. Okay, a dog whistle is about 30,000 hertz. Some people can hear that. I can hear dog whistles. Yeah, but yeah, there's really, really low bass would be stuff like an earthquake. Right? You don't really hear an earthquake, you feel that. Okay, if you had really, really deep rumbling bass, yeah, you feel that more than you hear it. Yeah. But about below, depending on your hearing range, and that narrows. Okay, as you age, you lose certain frequencies. Okay, and some people with hearing impairments don't hear certain frequencies. So then they require hearing aids to boost those frequencies. My son's hearing aids, they boost only certain frequencies. Okay, mostly the ones to do with S's and F's and those kind of soft sounds, because he doesn't hear those. Right? So it all depends on kind of the nature of your ear and hearing and stuff. No, I mean, I suppose you could, but remember, it's only going to boost things that you're actually capable of hearing. Like my son can hear those frequencies, but his hearing of those frequencies is limited, right? The frequencies we can hear is based on how our eardrum can move, all right? And so it can only move so fast, about 20,000 hertz. For some people, 25,000, maybe a tiny bit higher, right? For a dog whistle is almost smack in the middle of their hearing range. So it's something that they hear very, very well. Like when I say I hear a dog whistle, I can perceive just a tiny hissing, basically, right? Like I know when our dog's barking thing that's supposed to not be able to, it's supposed to make him stop barking by making a piercing sound. I know when that goes off. Right? I can hear it, but it doesn't hurt my ears because I can just barely perceive it, right? Whereas for him, it's like he runs off and hides under the bed. Okay, it's obviously well within his hearing range. Anyone else have a barking egg? If you ever want to stop your dog from barking, get this barking. It's just a big egg, and when they bark, it detects it and it emits this like really shrill sound that makes them like run away and hide and stop barking. Or get it for your neighbor's dog. Yeah, you can fix their wagon too. Okay. It's not cruel. It just makes them associate barking with this awful sound, and then they stop barking. It's Pavlov. It's just behavioral psychology. Okay. All right. So again, kind of back to this idea here, guys. Okay, back to this idea of if I want to design something like a concert hall or a home theater system or something like that, and I want where the people are sitting to have the highest quality sound, I need to make sure that for most of the wavelengths, they're going to perceive that they are going to interfere and overlap constructively where they sit. Okay, okay, I wouldn't want to have destructive interference at those places because obviously then the quality of the sound that they would hear would be poor, right? Okay, so like we were saying here, if there's a difference in travel of a full integer, so if we're looking at this situation here, this red dot, the waves have traveled from this speaker over here, 1, 2 wavelengths. They have traveled 1, 2, 3 wavelengths from the other speaker. The difference is still a whole number. Okay, it's a full wavelength difference, so they're still meeting in phase and thus interfering constructively. At this point, right here, okay, the waves from this first speaker have traveled 2.5 wavelengths, whereas the ones from the other speaker have traveled 3. That's a difference of only half a wavelength. So as a result, that would be out of phase, and they would hear destructive interference. All right, everybody good with that? All right. So here is how I would ask that question on a test. I always ask this question on the unit exam because it tests universal wave equation, it tests the principle of linear superposition, interference, okay, basically allows me to test all the stuff to do with waves. So I have this situation. The listener is here. Okay, they are 2.4 meters from this first speaker. All right, so this is speaker A. All right, and this is speaker B. They are 3.2 meters apart. They are emitting a sound with a frequency of 214 hertz. Okay, and the speed of sound in that room is 343 meters per second. I want to calculate whether that person hears a loud sound or a quiet sound. Okay, now remember, whether they hear a loud sound or a quiet sound is based on the number of wavelengths the waves travel from each of those speakers. So what's one of the first things I should calculate about this sound? If whether they hear a loud or quiet sound is based on the number of wavelengths the waves travel, what property of the waves should I calculate right now? Wavelength. Okay, it's the one thing I wasn't given. I was given speed and frequency. Okay, I can use the universal wave equation to figure out what the wavelength is. Ooh, that's awful. Okay, so V equals F times lambda. All right, I'm trying to solve for lambda, so lambda is going to equal 343 divided by 214. It's about to 1.6. Is that right? Yeah. Okay. So the wavelength of this sound is 1.60 meters. Okay. So whether they hear a loud or quiet sound is dependent on how many wavelengths there are between the speaker and the listener from each speaker. Okay. Can I calculate right now how many wavelengths there would be between this speaker and the listener if I know how far it is and I know the wavelength? Okay, how would I do that? I have 2.4 meters, and each wave is 1.6 meters long. How do I calculate how many waves there are? Just divide them. Yeah. Okay, so if I go 2.4 divided by 1.6, I'm going to get 1.5 waves. Okay, it's going to be 1.5 wavelengths. So essentially, this is what's happening here. There's one wavelength and a half. Okay, it's 1.5 wavelengths from that speaker to the listener. I don't know how long this is. Can I figure it out? Okay, just got to use Pythagorean Theorem. Okay, so I do Pythagorean Theorem and I find out that this side of this triangle is 4.00 meters long. All right, can I figure out now how many wavelengths there are? All right, I just go 4 divided by 1.6 and I think that comes out to 2.5, right? I think so. Okay, so 2.5 wavelengths. So essentially, there's 1, there's 2, and there's the half. Are they arriving in phase? They are. Okay. If I subtract those two, if I go 2.5 minus 1.5, do I get a full number, a whole number? All right, then they meet constructively, right? Because there's only one wavelength travel difference, or a full wavelength travel difference.
Are they always going to be halves?
Yeah. It takes me quite a while to make these because I have to make sure I get all the numbers right so it comes out to at least very close. Like it could be like 0.48. If it was 0.48, 0.49, it's a half. It's okay, so just keep that in mind, guys. I would never make one that was like it's 1.2 wavelengths, because then how are you supposed to tell me if it's constructive or destructive? It's sum of each, right? So it would either be a full wavelength or 2 full wavelengths or 2.5 or 3.5 or whatever. It would be definite. Okay, these are out of phase. These are in phase. It's constructive or it's destructive. Okay. All right, everyone follow how we did that one. Okay, so we do a universal wave equation calculation. Okay, we figure out the lengths, the distances, we figure out how many waves there are from each speaker, and then we determine whether they meet constructively or destructively. Hunter.
I was just going to ask, like, how would you say that figure? Like, I could count how many, but isn't that's why they have different.
That's why they have so many different speakers in so many different locations. The only way to really make up for that is to overpower it. Yeah, make sure you got sound coming from basically all directions at a high volume. Okay. If you go to a concert, how many people have been to the Windspear in Edmonton? Anyone been there? Yeah, like the Windspear Theater in Edmonton is like almost the most acoustically perfect building you'll ever be in. Okay, if someone is performing on the stage, they require very little electronic amplification. The building is just designed so that the sound waves, when they bounce off the walls, they meet each other, they interfere constructively. Okay? Very little electronic manipulation of the sound is required there. From the very back of the theater. Yeah, it's crazy. Don't be whispering to your friend on the front. Okay, like on the stage, everybody in the building will hear it. Yeah, perfectly clear. Yeah, it's an amazingly designed building. Yeah. Okay. We used to have the same problem here at the school. Okay. Not on purpose, but the bathrooms didn't used to have doors on them. Okay? When we first moved in here, the bathrooms didn't have doors, and it just so happens that the way the angle of the bathroom would channel sound from inside the bathroom straight out and into my classroom. Anything that happened in that bathroom, we could hear perfectly. Same for Mr. Dickey from the boys' bathroom. Okay, like we just had to have our doors closed all of the time, and once in a while we'd catch conversations we'd really rather not have heard. Okay, yeah. So be thankful there's doors on there now, because yeah, there were no secrets in that bathroom. That was not where you went to have a conversation. Okay. Oh no, yeah, we told people, and they got they would have a conversation. I'd try to get to the door to close it, and everyone would like wait to see who it was. Yeah, people figured it out pretty fast. Okay, so that's going to be kind of, this guys is a great example problem. Make sure you mark this in your notes somewhere. There will be one like this on your unit exam because it allows me to test all of the most important concepts, okay, in the wave part of this unit. Interference, linear superposition, okay, wave equation, all of that kind of stuff. Okay. All right. Remember that coming up for your simple harmonic motion assignments are due tomorrow. Make sure you have those done. Your pendulum lab the day after that. Make sure you have that done as well. Right? Unit 4 exam and West Ed assignment are next week. And then I'll back off of you. Okay? Because, well, it'll be done. And all you have is your final after that. Remember, your final also. Okay? June 22nd, that's a Friday, 9 a.m. in the gym. Okay? Make sure you are here for that and ready.